who is Professor Claudia Draxl. Claudia got her PhD in solid-state theory at the University of Graz, and from 1997 she started to work there as associate professor. Then at the turn of the millennium, she moved as a guest professor to Uppsala and came back first to Austria, when in 2005 got a full professorship at the Mountain University Leuven in Austria, and then moved to Berlin when she got a very prestigious position called Einstein Professor position at the Humboldt University in Berlin. From 2014, she is a Max Planck Fellow at the Fritz Haber Institute in Berlin. Claudia is a very successful scientist with more than 260 papers published, which were cited more than 10,000 times, according to the Google Scholar. Claudia is interested in solid-state theory, and in particular, she works on the theoretical spectroscopy, which means that she investigates an interaction between matter and radiation. She's also interested in the electron-photon coupling and the related phenomena, and today she will also tell us about the NOMAD project, because she is also involved in the material studies. And for her achievements in research, in science, she got a lot of awards. Let me tell the few, I'll name the few. In 2000, she got a honorary degree at the Uppsala University in Sweden, and she got also the Ludwig Boltzmann Award for theoretical physics by Austrian Physical Society. She is a corresponding member of the Austrian Academy of Sciences. And as I mentioned before, she was appointed as Max Planck Fellow. And today, Claudia will tell us about electronic structure theory, from this theory to the data-driven science. Claudia, the floor is yours.
Thank you. So thank you for the kind introduction. I also would like to mention that I have somehow connections to not directly to Poland, but at least Jacek, whom I know from my scientific childhood on, and somehow we crossed, or our ways crossed each other. So it's nice to meet him again. So, as you see, I'd like to talk how you get from electronic structure theory for material science to data-driven science, the connections between this, and then I'd like to discuss various aspects that are related to this. So, let me start from discussing a little bit the paradigm of our research. So, of course, many years or decades or centuries even ago, experimental science started, but it was much later, in the 1600-something, where the first equations popped up. So this established the second paradigm, the theoretical science, which of course never made the first one obsolete. So if I talk about a paradigm, it's not something completely new or something that we should use exclusively, but something that complements what we have already in hand. Now, having these equations, and also with the advent of very fast computers, we can solve these equations numerically, and this somehow opened a new branch of science, which is computational science and simulations. And now somehow we are on the borderline between this third and fourth paradigm, because these computational science tools, they produce a lot of data. And I would like to discuss what we can use, or how we can make use of this data in order to go to the fourth paradigm, which is data-driven science. So let me start out with our scientific vision. What do we want to do? Now, actually, I'm a computational material science, or a theoretical physicist. So what does it mean for materials? At a certain point, I think, we would like to be able to have maps which tell us where in the compositional space we find good materials for one property or the other, like thermal barrier coatings or superconductors or whatever. So we would like to have maps, like you have a map of Europe where you can distinguish between people speaking mainly French or Polish or whatever. So could we have something like this for materials? So, of course, the most important thing will be what do we call our descriptors? So what are actuators behind what makes a good material a good superconductor, or what makes a thermal barrier coating material a good barrier thermal coating material? So this, I think, is the big question. And at the end, I'd like to show you one example for how you can approach this topic and what these descriptors actually are. Well, let me go back in history again and actually show you one of our role models. This is a very prominent role model, namely the periodic table of elements. Exactly what we have. We have the columns and the rows, or the other way around, columns and rows, and for organizing the atoms, and they tell us actually what the properties of the atoms are. And now you have to think about when Mendeleev came up with this idea. So this was way before quantum mechanics was born. So in that sense, there was a genius somehow. It was a genius idea to arrange these atoms in the columns and rows, and which tells us basically about the properties without having the quantum mechanics background, which actually is the driving force or the actuator behind this. So I'll keep this in mind, and let's say this is a role model for what we want to do further on. So now let me get back to materials. I think these four paradigms of science not only valid for material science, so how do materials come into play? What are we interested in? I mean, if you look into any part of our scientific life, not only scientific life, but societal life, I think everything that we have in hands, be it a pointer, or be it a computer, or be it whatever, needs a good material behind. Okay, so material science is a very important field for novel inventions. So, for instance, think about the tools. Now we have, hard tools and hammers and so on. We want to make them better. I think this is the nature of human being, that we want to have everything better than we have it right now. So we want to have things harder and tougher than they are already. Now we need, I think, aircrafts and cars and things like that are lightweight because they consume too much energy. And lightweight materials, of course, then you have also lighter bonds or less strong bonds, and they break. So we would like to have materials that are light, but at the same time ductile. Yeah? So, and heat resistant. Think about our turbines, basically. They run over melting temperature of the materials, basically. So, or our electronic gadgets. So here you see, for instance, a phone that is curved because we want to have it flexible. We would like to have it even thinner. Non-toxic would be good. Sustainable would be good. So there's a lot of challenges for material science, also for lighting. Should also be energy saving. I think going from the light bulb to the LEDs has already reduced the energy consumption a lot, but there's still a lot of room for improvement. They still consume too much of energy. Or even in medical applications. So if you think about artificial hips or teeth, they must be biocompatible, but they need to have the materials properties that we would like to have them. So there's a lot of room for new materials. And, well, you might ask a question how theory comes into play. Because typically, people would somehow grow such material or synthesize a material in the lab and would measure and then see if it's useful for an application. Now, theory actually is able right now to treat such materials properties from first principles even. That means without any parameters, and predict these materials with very properties with very high accuracies. Again, this goes hand in hand with experiment, of course, yeah, that way we can explore different properties and materials in very deep detail. So, what about computational side of this? So, how do we solve this? I mean, the ideal case, of course, is it's all about Schrödinger's equation. You just need to solve this very simple-looking equation, right? So, in principle, you do this. The question is where to find this wave function. This is a many-body property, which is very cumbersome to achieve. I mean, from a mathematical point of view, it's an NP-hard problem, so we will never be able to compute this directly right away for a complex system like a material. Well, So how to find it? One way would be to go to Sweden, because as you see here, even in 9101, this was again before the advent of quantum mechanics, in Sweden they knew how the wave function of steel looks like. So, but there's not many wave functions that we have in hand right now, so we have to come up with something simpler, or something that we can solve. And now this brings me to the, let's say, workhorse of material science, which is density functional theory. So this is basically what in practice we solve on everyday basis on our computers. Because it's an ab initio theory. Ab initio means that it doesn't rely on any parameters, and we can treat atoms, we can treat molecules, but also clusters, bulk materials, surfaces, interfaces, and any kind of nanostructure on the same footing. So we have one equation, again it's not the Schrödinger equation, but the Schrödinger-like equation that is able to compute or give us the properties of all these very different systems. So the only somehow input that enters here is the number of atom and the kind of atom that is involved in the material. And this is nice. So how does it look? I just give you a crash course, so there's one transparency on the theory behind. So it's a ground state theory. So and basically we solve, as I said, some Schrödinger-like equation. But now you see the wave functions that we have here, so the Kohn-Sham orbitals, they only depend on one coordinate. So they don't depend on all the electrons and the nuclei that we have, but this is just a very simple looking one-body Schrödinger-like equation with an effective potential. So it's the external potential, which is given by the ions. It's the Hartree potential, which is the classical electron-electron interaction, and the rest, the quantum mechanical bit of the electron-electron interaction, is cast into this exchange correlation potential. And it's actually the only approximation that we have to make. We should admit this. Now, why or how can we go from this very complex many-body problem to such a simple equation? Well, because it's written here, we replace this many-body system of interacting electrons by a fictitious system of non-interacting electrons. So we have here actually, unfortunately, we can see it. So there should be arrows between all of these electrons, which tell that every electron is interacting with the other by Coulomb interaction, of course. And you can be, okay. Yeah, you see. And we replace this by a fictitious system where the electrons seemingly don't see each other. And that's why having a non-interacting system at hand, we can get to such a simple-looking one-body equation. So, and the nice thing is what they have in common, this system and this system create the same electron density by summing up overall occupied single particle states. So that means that with this simple equation, we can have access to the properties of the many-body system. So there's one thing we have to be cautious about is, namely, by boiling this down to this simple system, we are not justified, so to say, to interpret these single particle energies and wave functions in terms of real single particle energies or quasi-particle energies and wave function. This is something we need to keep in mind. But having the density in hand, we have access to all kinds of materials properties. So, and this brings me to the first time to the data aspect. So what you have seen, just I walk you slowly through this, is that we can, with the input, which is just the atomic positions and the nuclear charges, we can use density functional theory to compute the total energy, the electron density, potential, wave function, so all kinds of observables we can compute out of this. Now, as I also said, we are not allowed, basically, to interpret the single particle energies. So if we want to go to excited states or to spectroscopy, we have to employ other theories. I'm not going to introduce this because this would spend basically the whole time. So, but I just mentioned this, for instance, many-body perturbation theory, which gives us electronic structure and spectra. We can use density functional perturbation theory, which would give us phonon spectra, for instance, and thermal properties. We can do ab initio molecular dynamics that would introduce temperature into the calculations. And then you see the amount of data that we create approximately here when computing just one material. Okay. Interestingly, at the end of the day, sometimes we have to compute quite a bit, but we are just interested in one number. Or what is published is sometimes only just a graph or a table or something like this. And most of these calculations are basically forgotten in between. Because, for instance, if you think about a thermoelectric material, what counts at the end is the thermoelectric figure of merit. Okay? So this is the quantity that tells us how good a material can be used in order to get waste heat back. So it would be very good to have thermoelectric materials with a high efficiency such that we can use all this waste heat that's produced in all our machines, turn it into electricity, and that way save a lot of energy. So it would be nice to have. And this actually, I mentioned this because I would like to exemplify, so to say, how complicated it is to get this number. So I also would like to say that there is many people now on this planet who use all these methods and solve all kinds of different problems. So the amount of materials that are computed actually wherever in the world, this is really growing exponentially. There are many, many projects, many applications for our theory. But we also have to say that most of this is basically thrown away. And this I would like to exemplify with the example that I just mentioned, this thermoelectric figure of merit. So what do we need for this? A thermoelectric material should operate on a large temperature range. Why? Because in any machine, there's a lot of heat generated. So if you want to get rid of this heat, you have to somehow find a material that can operate over large temperatures, a few hundred degrees centigrade, something like this. So whatever we compute, basically, we should compute as a function of temperature. And this is the geometry of the materials, so how the atoms arrange. This is the phonon spectra, thermal conductivity, then electrical conductivity, because the figure of merit is basically the ratio between these two. And this also tells us why it's so complicated to find a material. That's good, because if we increase the electrical conductivity, also the thermal conductivity will increase, because it's the same electrons basically responsible for that. So, but it's just a side remark. So now we have to compute all this. So we employ density functional theory, many perturbations here probably for getting electrical conductivity, density functional perturbation theory or molecular dynamics in order to get the phonon spectra and the thermal properties. And that means that you create, even for one temperature and for one material, this amount of data in order to get at the end one number out. And this is very inefficient. So the question is, should we compute all this again? Because we have solved the whole quantum mechanical problem. And if you just publish a number at the end, probably someone else could use this data for a different purpose or doing similar things. So I also like to mention there's many initiatives right now available on computational high throughput investigations. That means you can, on the computer, you can vary the material, just changing the atoms, the composition or so, and then see how the properties change. And you can do this for many hundreds or thousands materials. And finally, you do this, probably you find two candidate materials that are interesting, and everything else is thrown away. Probably 1 out of 1,000 is kept. And I think you can learn also a lot from those materials which are not so interested, because you know why they are not working. So I think there's a lot of information behind that. So this was actually the reason why we started to establish a computational materials repository. This was, I think, 5 years ago, 2014. We put it at the end of 2014 even. We put it online because we thought it could be useful also for people from outside, not only from our groups. And since then, we have collected more than 50 million open access calculations. So now you could look up who has done which kind of calculation, what is already existing, and maybe use the data for your own purpose if you want to do science with that. Now, you can do science with this, and this is what I mentioned at the beginning. So at the end, our aim is to learn from this data. So not only learning from the individual studies that we want to do anyway, but also learning from all the data that are available here. And I think that one of the prerequisites for being able to do so is to be fair. Okay, so if you're not familiar with this, fair means findable, accessible, interoperable, and reusable. And very interestingly, this paper, which defines these fair guiding principles, came out in 2016. So I think it was much later than we had started to use the same principles or apply the same principles in our field. But as I would like to point out, you will see that what we have put up, the infrastructure that we have put up, corresponds very much to these fair principles here. So let me walk you a bit through these fair principles. What does it mean? So what does the F stand for? Mentioned already. F means findable. Okay. So it has a very practical aspect of. So Nora, my PhD student, just finished her thesis. The question is, where do I find her data if I need them? Okay, maybe she's publishing a paper now, but all the data somehow will be either spread on her computer or somewhere else. So all the other people, they're working on the individual computers or on clusters or at supercomputers. And will I be able to find any of this data again in a few years? So in principle, by law, we are requested to keep data for 10 years, but how do we organize this? So in that sense, putting such data in a repository is also very useful or very practical from the group point of view. So in that sense, as I said, we opened up this repository, so everyone on this planet could, from a local computer, upload the data to this central storage, to the Nomad repository, and then this data are saved there for at least 10 years. In practice, it will be much longer. Okay. So we're getting organized. What does A mean? A mean accessible. So once you have uploaded, you want to get them back. So we need to make sure that they're accessible again. Okay? So in that sense, everything now is sitting in this database. And if you have a closer look, then you will see that everything is organized in files. So people have uploaded files, people can download the files, you can download the files, and if you're an expert, you can use these files. These are input and output files of many, many calculations. But I think we can do better, and in this sense, we have already developed the services that can also be reached by APIs, which allow you for automatic download of the data somehow. So what are they? And here I would like to mention the Nomad Encyclopedia. I like this project in the sense that it's not only fun, but I think it's also useful, because think about these 50 million calculations. They're sitting in files. As I said, the experts can use them because they can download and repeat a calculation or build on top something on this calculation. But can also experimentalists use this data? So then files are probably not very practical. So we had in mind, once these data are there, let's show to the public what the content of this data is. So for instance, you go to this graphical user interface, you pick iron and oxygen or whatever material you're interested in. Then you search, you get a list of materials. You can also search for structure, for properties, for all these things that we offer here. You get a list of materials, and you pick one of these materials you're interested in, and then you will see what people have calculated. So you can access it also from a human point of view, human-readable point of view. So you will see the details of the structure, the details of the electronic structure, if someone has computed the band structure, density of states. You get the details of the methodology. Actually, these pluses here mean that you can get more information if you refine this. You can click in here. Also, you can get thermal properties like phonon dispersion or specific heat or free energies, things like that. So, and then you see this tree here. So you can select calculation. You can select, for instance, the exchange calculation functional. You even can select the code that has been used to produce this data. And then you can compare different calculations if you like. So we also have developed advanced graphics tools. And one thing I like particularly, this is the virtual reality tools. So it's not only that you can download the structural data from the repository and then view it with simple Google glasses or a cardboard or with a full VR environment, but there's also some movies that we have produced, and you can somehow use your smartphone inside this Google cardboard, and then you watch these 3D movies which are uploaded to YouTube or whatever. And I think what you see here, this is one of my favorite examples. Well, it's two pictures, of course, because you don't see it in 3D here. But this is an example of an electron hole pair. So if you shine in light to a material, then electrons is transferred from the ground state to some higher energy state. And this electron that is now somehow excited, and the hole, or the missing electron that it leaves behind, they attract each other by Coulomb forces. And this gives rise to a two-particle state, which depends on the coordinate of the electron and the coordinate of the missing electron of the hole. And you cannot visualize this six-dimensional object on paper on a screen. But in these virtual reality tools, you can somehow choose the position of the electron and then see how the hole somehow is distributed around this or the other way around. So it gives you access to quantities that are hardly accessible otherwise. So, but you can also use this, I mean, this is a service, if you like, for people who want to see what people have calculated. But I think we can also learn from this tool. For instance, to find similar materials. This is a simple example, it's gallium arsenide. But I just want to mention another example. Think about this new solar cell materials, the perovskites, which contain lead. Okay? So you don't want to have lead. This is toxic probably in your device. So you may look for materials that have certain features in common with this other material, but are without lead. I mean, in the future, it should be possible to search for this. Now, let me see what we can do here. So I choose gallium arsenide as a reference, and I search for materials that have a similar density of states, so similar electronic structure. And then I search in these 50 million of calculations, and then I find, for instance, gallium phosphide or antimony carbon. So and this TC here is the similarity coefficient, which is between 1, which is high, and 0, which is pretty low. So this is pre-computed at the moment. So I think it's probably online, or not yet, but it should be online soon. So if you look up a material, then you can click a button, and it tells you what are the most similar materials to the one that you have created or have looked at. And in the future, we would like to develop a tool that allows a user to, for instance, zoom in onto a certain range and ask for materials which have a very certain feature in common. Because, I mean, probably it's not so interesting to have the whole electronic structure very similar, but some feature that's relevant for a property that I'm interested in. So, well, another thing. Let me proceed to the next task here, and this is the analytics toolkit. So we're getting closer to these artificial intelligence applications or data analytics applications. So we have already somehow developed a few tools which allow us to use the data in order to make predictions, so to find out what these actuators between or behind materials are. So if you look at the web page here, you will find tools. These are online tutorials, for instance, for crystal structure prediction or predicting certain properties, or error estimates or classification of materials. So there's quite, I don't know, 20, 30 of these applications are really online, which can be used and everyone can play with and explore the methods behind that. And there's no need to install software. It could be used right away. So also the computation is done in the background, as long as it's not too heavy. I have to say here, you don't even need to register here. And the idea is, as I said, our vision to finally somehow separate different materials in their composition and their range in order to find out where on this space I can find these materials for a certain application. Now, of course, this is a very far-reaching goal, because this would be heaven, so to say, to develop this. But I would like to show you one example how we approach this. and where you can see that in principle this works already for simple questions, of course, but yeah, I'd like to show you how this works. Now, think about, I give you two atoms, A and B, and you ask the question what kind of crystal these atoms would form. So would it be, for instance, a rock salt crystal, or would it be single-banded? So they distinguish between the coordination around the atoms here. So what would they form? And this is actually an example. It's called the Phillips-van Vechten problem, because they have asked this question already in the late 60s or beginning of 70s. So many people have worked on this problem. And the question is how to predict what the crystal structure of just such a binary alloy would be. So in other words, can I find descriptors? So descriptors, as I said, are the parameters that describe a certain property of function best. Could I find such descriptors that allow me to separate rock salt and zinc blended structures from each other? So what would this D1 and D2 be? So it could also be higher dimensional. There's no need for having a 2D descriptor. Okay? Of course, I mean, looking at the maps that we have in mind, this will be very highly dimensional, because there won't be two properties or two simple things that would give you this map. So I'd like to show you the solution of this. So what we have done is we have computed all possible octet binaries, and there are, I think, 71 out of, no, 82 out of this. And we've computed the energies, or the energy difference between rock salt and zinc blende. And what you see here is everything what is in favor of zinc blende, having the lower total energy, would be in red, marked in red, and everything what is in favor of rock salt would be marked in black. And everything where the total energy difference is so small that these materials hardly can decide what they want to be, this is green. Okay? So this is the color coding of this. And there you see that we have already now two descriptors, T1 and T2, that allow us to do so. So in comparison to previous solutions, we're even quantitative, because we tell you how far away we are from the separation line. And the nice thing, and I'll show you this in a minute, is that we don't need properties of the material itself to predict what the structure of the material would be, but we only need the properties of the single atoms. And this also distinguishes us from previous calculations, which employed to know band gaps and dielectric screening and things like that. So you would need beforehand to know the properties of the crystal in order to know what the properties of the crystal are. So in that sense, we have more predictive power. And I'd like to show you how we achieve this. So this map, so to say, of these binary semiconductors, for this we used compressed sensing algorithms. So this is something which comes from visualization pictures and these kind of things, to boil down a lot of information to the most important few quantities here. So this is the way we get our descriptors. So as I said, the predictions are just from neutral atoms, and also this example you can find on the analytic tools kit. So you can play with this and see which are somehow the parameters that are really important for getting these properties. So if you're interested in what our descriptors are, in this case, it's the ionization potential and the ionization affinity of the two materials of these two atoms, and these R's are these radial distributions of the p-like wave function, for instance. Of course, the wave functions of the atoms are decisive of what kind of bonds would be formed. So looking at these parameters, somehow it makes sense to why this pops up here. You may still ask the question whether such an equation that we get basically corresponds to a law or a formula. It's something we can discuss, actually. But it's the descriptors or these parameters that are useful for predicting these kind of properties. Now, let me very quickly demonstrate how we build this model, how we get to these results. So we have to train, of course, need a training set. That means we take this 80 whatever materials that we have, we compute the properties of interest. In this case, the property was the energy difference between these two structures. And we compute this for these many materials. Now, that's first step. The next step is that we need to come up with an intelligent choice of features. So at this point, I would like to tell artificial intelligence or machine learning tools, so to say, is not something that you can use from the shelf. So you cannot use Amazon or Google or whatever tools and just apply it to material science. It won't work. So in principle, you can learn the Schrödinger equation, but it's much too complicated. So we will never have enough data in order to learn this. So in that sense, we have to somehow make a choice before we employ our tools. So we need to come up with the feature space with our descriptors. So then the next step, we need to learn. So what is the relation between the property and these parameters? So we would like to learn this P of D. And as I said before, for doing so, we have employed a compressed sensing method. For instance, lasso, but you can use something similar. Okay. And then you see, you can predict more materials. And of course, you will never train or shouldn't train your machine on all the data. So there should always be data that are outside this training set, such that can you probe how good your predictions are. So you look at the cross-validation score, and maybe you can refine your search, producing more data in order to refine if available. In this case, there are simply only 82, and that's it, so you cannot produce more materials. But it worked even for us. So, as said, the most important question is now how to create these features. Yeah? So, free atoms. So we came up with ionization potential, affinity. So somehow this tells you how much energy it costs to either don't give away an electron or to dissolve accept an electron. So which are decisive parameters for forming bonds. Also, as said, for instance, very important are these radial distributions of the wave functions of the valence electrons here. We also offered properties of dimers because they have already some information of the bond built in. Interestingly, the machine didn't need it, so we could get along with just the atomic properties here. But then, of course, if we go back here, these are just a few quantities, 20-something, okay? So this is not good enough. It's not a rich enough feature space in order to learn. So what we do then, interesting, we're a little bit behind on this slide. Okay, I need to go here. So we came up with all kinds of nonlinear combinations of this. So we add and multiply and take to exponent, and so of course only if physically meaningful. So we shouldn't add quantities with different units or something like that. So this is the to construct this feature space. Now actually we went up to 10,000, 100,000. You can go to millions of such configurations in order to allow your machine to learn. And then we learn the linear relationship. So actually, we put all the nonlinearities here into the feature space because we want to learn finally a linear relationship that's easier to interpret, if you like. So in learning this means that we search for the minimum error here, and this is where compressed sensing comes into play, because we use the L1 norm in order to boil down the number of descriptors to a small quantity. So now this is so far the F and the A, how to access this. Now, what does the I mean? Okay. I means interoperable. So, and this is getting more tricky because I told you we have 50 million of calculations now. So are we really sure that we can use all this data together in order to learn from them? Because all of them come from different sources, they have individual errors, and this is a highly relevant scientific questions we also work on. So let me just show you here. So what we support are 40 different codes. So you may use any of these codes here and even more. So these are those with the most data in the repository. And upload the data. So we will accept all input and output files. Our machinery, the infrastructure, will detect the code that has been used in a certain file and then upload the data to the repository and save it in the database. There you see already how rich this ecosystem of our environment is. So, as a next step is we normalize this data. So all of them come with different file formats, with different units or so. So it's quite natural. We want to have them all in the same form. That's why we have also a version of this, and this is what we call the Nomad archive, that contains the normalized form of this data. And then you can operate already on the whole amount of data here. Very crucial for this. And I think this we completely underestimated, and I think even everyone else probably underestimates, is the description of the data, the metadata. So I think this is really important, and that kept, so writing the parsers and the metadata, so that kept around 20 postdocs for more than 1 year, maybe even 2 years busy, because we need to make sure that a total energy that comes out from GPO is comparable to a total energy that comes out from QBox. Or sometimes in different communities, people use the same word for different quantities, or use different words for the same quantity. So it's very, very important that we know exactly what the code produces and what the quantity and the property is about. But this is done, and I really wanted to highlight here that we have done it for the community, because putting this burden to the code developers would never work. Sometimes these are small groups, so there are 1 or 2 or 3 people developing a code, and they want to do science, and they don't want to think about an infrastructure and to normalize data. So I think that's why we said, let's go for it, let's offer this, and now this data infrastructure does so, and then people can use it all over the world. So somehow we can use now all this data together, because they are in the same formats and the same units. The question is still, what about the quality? Is the same quality? Of course, you compute things with different computational parameters, and so how to compare. And here I would like to take a step outside of Nomad, and but as you will see, there's a few Nomad codes that have contributed to this, and come back to a research paper that we have published together with many, many others. I'll show this in a moment here. So how to compare, or how to make sure whether 2 or 3 or 4 or 5 different codes that seemingly compute the same thing really compute the same thing. So do they give you the same answer? So now, and that's why I've written the Kohn-Sham equation here. So this is the equation that all these 40 codes solve, but they solve it differently. And so, for instance, they use, and this is probably the most important thing here, different basis sets in order to expand this quantity. Okay? So this is crucial then. By plugging in such an ansatz, you end up with a generalized or normal eigenvalue problem. And this is what all the codes are doing. But of course, the quality very much depends on the computational parameters. So how many of these wave functions, of this basis function, do you use in order to produce your results? And I like to point out here, so this, I'm not talking about the accuracy, okay? The accuracy is hidden somewhere in this functional, okay? I'm talking at the moment, I'm talking about the numerical precision. Okay? So, and this is what I wanted to point out. So this was a community effort published 2.5 years ago or so. And this was driven by Stefan Cottenier from Belgium, together with his PhD student Kurt here. Mention these 2 people who have been involved in my group. So as I say, this paper has more than 60 or even 70 authors. It means really the whole community contributed to this. And the only question was, how reproducible are such density functional calculations? Okay? So how precisely can we solve them? It's also called the delta test, actually. So it's very simple. You take one code, and you compute the energy versus volume. Okay? You take another code, you compute the same thing, and then you evaluate by a Birch-Monaghan fit through this curve. You evaluate what the difference between these 2 curves are. So we go through the whole range here, and then we add up, we sum up all the somehow uncertainties between them. And this is what we call equality factor. So this is a number that we get for a given material and for a given pair of two codes. Okay? So, and then you can do this for many materials, like it was done in this paper. You can average over this, and this is what we get. So you can go, either you look up the paper, you go to this web page, and then you choose your favorite code, and then you see how different, what this quality factor is by looking at the list of these many codes that we have available here. And very amazingly, you see, this is milli-electron volt, so the first, I think, 12 or 13 of this are within half a electron volt per atom. So it's a very, very small difference, or you could argue, well, all the codes really give you the same answer. We have to say so, this was an effort of a few years in order to get most of these codes there. So they changed the potential, they changed the approximation, also the numerical accuracy in order to get there, but now the results are actually very, very impressive. Now, of course, since we develop exciting, I put exciting on top. You can put any of these codes on top, but I like to point out there's a good reason for putting such a code on top, because this is a full potential all-electron code, like all these two others are, and you see these differences are really, really small. And full potential all-electron means that we don't have any approximation, further approximation inside, so there's no pseudo-potential involved. So the Conjem equation are solved here very precisely. There's no approximation for deep blank core state, so we solve everything very precisely. So that means that now we find really excellent overall agreement between the codes, which is really great, but it's just the beginning, because, I mean, this delta test, these were very simple materials, just elemental solids, but I think other systems and other properties will be much less forgiving. So if you look at defects or molecules or surfacts or so, I think the systems are much more demanding what concerns the numerical calculation or probably the approximation. Also other quantities like gaps, barriers, or spectra, I think are much more demanding in terms of the precision here. So this is something where we really have to work on in the future. You also see, for instance, that there are larger discrepancies for certain elements. So what we have seen before is just the average over this. So there's, I think, ongoing work along these lines in order to make sure that the same quantity is really calculated with similar precision in different environments. So let me finally get to the R, which is reusable. Well, think about one material. There are many different applications possibly. For instance, I mean, I'm mentioning lighting. So tungsten has been used for light bulbs before, but now it's one of the probably most interesting candidates for fusion reactors, because it has the highest melting temperature for radiation shielding. So if you have investigated somehow one property, someone else may use the same data, the same calculations for something completely different. So there's no need for computing this again. No? Or titanium dioxide. I'm interested in theoretical spectroscopy, so I like to test my methodology that I develop for titanium dioxide, because it's a very critical material. But at the same time, it's used in heterogeneous catalysis, or it's a component in dye-sensitized solar cells, or if you go out to sunshine, it's the white in the paints and the sunscreen. So again, very many different options how to use the same data, and I think one person working in one area probably is not working in the other, so someone else could use the same thing for something completely different. And as I said, I mean, we have solved the quantum mechanical problem. There's a lot of information in this data, we just need to use it. So, well, if you look up, we use repurposable, so use the same thing for different purpose in the FAIR paper, the word reusable. So the reusable sounds a bit like second-hand, and so I would like to avoid this. Okay, so what are the next steps? Well, I mentioned already that this project was created out of a probably bilateral project we had a work together with Matthias Scheffler from the FHI on thermoelectric materials. This is how the whole thing started. Now then we put it online. Then we made a bigger effort out of this. So the last 3 years we had funding from the European Union. It was the NOMAD Laboratory, which was a European Center of Excellence, with 8 scientific groups with very complementary expertise, from electronic structure to quantum chemistry to force fields, and also having 4 big computing centers on board. Yeah, and now we even made a further step, in the sense that we, in order to make it somehow, give it permanent funding, we founded an association which is called FAIR Data Infrastructure, FAIR-DI, for physics, chemistry, material science, and astronomy. Here, it has various components. One is there, well, let me go back, is the computational material science, which is what we've just talked about. But there's also experimental material science, soft matter, astronomy. Well, now we also have a catalysis pillar already made up. So the thing is growing, and there's a lot of interest from many different communities. Yeah, so this is the next step to go. We're also part of this Go Fair, which is the European initiative of the European Science Cloud. And with this, actually come to the end. I don't know, probably I'm already over time, or should I show you the movie? A little bit. Then I skipped the movie, or I have a short movie, but I can skip it.
Okay, so you can run the movie.
Yeah. Okay. Let me see if it works. Oops. Somehow.
Did you know that we can design materials that don't even exist in nature yet? We just need computer simulations and data. More exactly, we need supercomputers and lots of data. Luckily, scientists have been generating materials data for many years. Actually, more data than we can handle, especially because it's disorganized and scattered around the world. The NOMAD project was born to solve this. NOMAD starts with a repository aimed at collecting all of the possible computed materials data in a comprehensive database. It already contains millions of calculations accessible to researchers and companies, all converted into a homogeneous representation, the NOMAD archive. In this docile form, vast swaths of information can be efficiently analyzed by machine learning and other data mining tools, generating knowledge that will help discover new properties and new materials. Indeed, the sophisticated algorithms developed by NOMAD researchers are patiently digging through millions of calculations, classifying them, estimating errors, trust levels, and most importantly, finding trends and patterns that humans would miss because of the daunting amount of data. Myriads of CPU hours have been spent on computational materials research. The NOMAD tools are making them enormously more precious. However, NOMAD provides researchers with a comprehensive materials encyclopedia where they can find all the properties of any material in the archive. Data and results can also be explored visually through advanced graphics, charts, and 3D representations, and even with virtual reality applications, which let you see materials from the point of view of an electron. The NOMAD Center of Excellence brings together supercomputers and scientific insight to foster the discovery of new materials. Would you like to create what the future will be made of? Find out how at nomad-coe.eu.
Show you several aspects of what you can do with data, and this is also a very lively and interesting field of research, and I'd like to thank you for attending.
Thank you very much, Claudia. So, questions, comments to Claudia? Welcome. So maybe I will start. I mean, you admit to this database the results of certain set of codes. How do you select them, really?
I mean, you see, we have 40 parsers, so we've selected them how they're used in the community. I think these 40 represent pretty much everything, or nearly everything, what is used. And if there's a new code popping up and then people are interested, for instance, 2 weeks ago we had an advanced user from a different code who said, okay, I would like to have mine parsed. So he came and we developed together the parser. Now it's also online. So,
but you somewhat screen these codes. I mean, how good
we
they
know,
are, etc.
We know, we did a statistic before, which of the codes are used by the citations. This is even published, this is online. And then you see what are the, and we went for all of them.
And does it mean then afterwards, I mean, if you run your technology, I mean, you can provide numbers for a given properties with theoretical uncertainties, systematic theoretical uncertainties, or this is not yet available?
I mean, I've talked somehow how to make them uniform. I have talked about numerical position. What I have not talked about is the accuracy. So as I said, we have one approximation in DFT, which is this exchange correlation functional, and that may be decisive for many things. So one thing is that having many data, we also learn what is good. So what functional is good or good enough for a certain property or a certain material class. I think this also allows us to learn this. So that at the end, I even could show an example. We try to assess this as well, and at the end give all this data a kind of an error classification, saying this is this numerical error, may have this numerical error, this may have this error in terms of a certain property. This is somehow also a longer term goal to somehow to quantify the quality of data.
Okay. Questions, other questions, comments?
I have a question of an ignorant, because I'm a particle physicist. And we are doing, as I understood you, the same thing for many years now. And we have the training samples, which are huge and multidimensional. And then as a test of a proper learning, we have standard correlation plots between so-called truth and the final result. And that can be multidimensional. Could you show an example of such? Because your delta test was actually one number. And as such, it smooths over several correlations. But if we could see such
what you see here, it's not necessarily, you can boil it down to a number, but it's not necessarily a number, because this was averaged over all elemental solids, such that to have one global assessment for this. But if, for instance, you see here, you can somehow split this up and assess this accuracy for different elements. So oxygen, for instance, you see that the spread is different. But as I said, we are working on this by also quantifying the uncertainties for other properties and other materials. This is something which is still ongoing, and probably compared to other areas, material science is more complex because we have so many different properties, so many different materials. So there's a lot of different aspects to explore, but you're completely right. We have to go in this direction, and we have to systematically work on this.
Your talk had, in fact, two parts. The second one was about Nomad and this management of data. But I would like to ask a question concerning the first part, the calculation itself. It seems to me, well, maybe I'm wrong, but it seems to me that you are doing what I would call lattice QED. Because in particle theory, chromodynamics is too difficult to be solved analytically. So there are calculations made on lattice, just in different points, and then from there we try to guess some materials. So what you are doing is approximately the same, but with QED, because the only interaction that enters here is an electromagnetic interaction. That means QED. Am I right or wrong?
Well, I think material science is somehow simple in the sense that we only have Coulomb interaction between these particles, so it is electron-electron interaction. The problem so is it makes it still an NP-hard problem. It's the only interaction, but it shows up in very different facets. So it could be spin, it could be spin-orbit coupling, it could be vibrational coupling, whatever. So it shows up in different materials and different properties very differently. So it's very hard to grasp. And as I said, it cannot be solved exactly because every electron and every nuclei interacts with every other. We don't solve it on the lattice, so we boil it down to this effective one-body Hamiltonian with the one approximation inside. And we don't, in most of the cases, we don't solve this in real space, but in K space. So we sum up over many different K points to get the density finally.
Okay, you showed here a comparison between different codes. So you somehow certified that all these codes give the similar results. But what about comparing the results with the real measurements? Because this is the crucial point. We can have, 10 simulation codes which calculate the same bad theory properly, with the same accuracy and precision, but does it really feed the data
thanks for
from
asking,
the
because
experiment?
this is what I wanted to add before. Actually, yeah, you're right. So we are having one approximation, and the question is, how good is this approximation compared to reality? Now, what is reality? Okay, if you take a sample, and this brings me also to the experimental science. What's this? This is a glass. Okay, this is a glass. So this is reality. So the question is, first of all, how to quantify the uncertainty in experiment, how to quantify the difference between theory and experiment. So in that sense, we are at the moment, I don't say this should be done forever, at the moment we are on the safer side in order to get the accuracy to go to higher level methodology. So we know we go from a local density functional to a semi-local to a non-local one to from a whatever the Mercedes of density functional theory is. Then we can go to wave function based code like coupled cluster theory. Then we know how we can get systematically better, if you like. Okay? And for some properties and some materials, some approximation may be good enough. For other properties or materials, you need the best thing. But then you know exactly what you have solved, namely this electronic problem of the system, okay? Of a perfect material which is well defined. So what about experiment? Experiment comes with a sample which has a composition which has been treated under certain temperature, pressure, whatever. So depending on how you treat your sample, the properties may be different. Depending on the amount of dirt you have inside, the properties may be different. So experiment, and then experiment not only has the electronic interaction, but probably has also interaction with nuclei inside, so electron-phonon coupling, which we left out here. So we need to systematically approach these two sides in order to make sure that we're really talking about the same thing. And this brings me also to the problem of, as I mentioned at the end, that we're also going into experimental science now. So what is our input file corresponds to the sample. So we need a very proper description of the sample to tell what has been really measured or what kind of material has been really measured. Is it the material that I've calculated? Okay? So then we need to quantify or to describe also the measurement. So the apparatus has a certain resolution. It has been measured under certain temperature, pressure, whatever conditions. So the measurement corresponds to our code, if you like. And then, of course, the measured data correspond to our calculated data. So I think there's some way to go in order to make sure that we don't compare apples and pears, but we compare apples and apples from both sides, from theory to get more and more accurate and to include effects that are also present in experiment, and from the experimental side to give us a very detailed information what kind of material has been measured under which conditions. And then we can this is the truth, okay? The final truth.
Okay, I agree that this is the final goal. But you cannot wait with this comparison till the very end, because it can turn out that you have a perfect tool to describe apples and you have pears in your basket. So,
no, I mean, I don't say that we wait for the end.
You showed this simulation of which crystal structure is preferred depending on the two components. This is something which should probably be easy to check experimentally.
No, this is solved, yeah, but you don't know if you have a, let's say, a composition, aluminum 25 and silicon 75, you may have 1% of carbon inside, and this changes may change the properties completely. So I think we should be very careful in comparing.
I'm also a particle physicist, so this is not my.
No, I'll just remind you. Okay, steels is a very important material, and the different types of steels they distinguish really in the per mil or percentage.
Can I try?
Give it different properties.
Okay. I'm sitting on the last bench because I'm engineer as a master degree in physics in engineering. And then I went to physics and then to engineering back. And still starting with your first slide and paradigms. I'm a kind of cosmic satellite sent to the space 20 years ago or 30 years ago, and still using BBC computer on the board, which means I use only this language and cannot communicate with the megabytes or gigabytes, okay? And then my thesis, habilitation, was with the name of Matthias Scheffler at the end of my reference list, which means I probably confirmed one of the results of his calculation. And still there is no, response that this finding experimental is interesting to the theory community, which means for me it looks like we have two parallel universes which do not communicate too much because the experiment is too difficult to understand, and theory for theorists and theory is too difficult to understand for experimentalists who works with just solid state, okay? So my comment is whether it is still possible to communicate with people who really deal with materials, say, technology and engineers. Do they really request or ask questions which can be, solved in this, say, relative communication? Because when I went to Samsung and presented my CV, they said, if you can solve one particular problem which we have at the moment, probably they will talk to me, and if not, they were not interested.
I think, of course, we can communicate. We do this on our daily life basis. So we are working with experimentalists and asking questions together. And this is also the reason why we have here different pillars, because we started already with some examples with electron microscopy and other experiments to do something very similar for the experimental side. And the goal is, for instance, I showed you the encyclopedia, to bring these two things together, to show experimental data alongside with theoretical data based on a very good characterization of the calculation and the experiments. And I think if we can get better and better with this, and of course we need to bring these things together, and I think it is possible. There have been materials predicted which were by some groups which were synthesized later and turned out to exist. So I'm not so negative on this. With my former comment, I really want to point out that we need to be careful what we are comparing. But if we know what we are doing, I think this is perfect. I love to work with experimentalists, so I don't want to avoid this.
I have actually one question and one comment. The question is the following. You have shown relatively simple systems which you have in your database. And the question is, do you have experience regarding the quality of calculations when you have heavier elements and you should account for relativistic corrections into the exchange correlation functional, and how well these packages are doing?
I mean, this was the reason I put here all electron codes on top, because all electron codes treat all the elements on the same footing. There's no approximation to the potential, so we can treat hydrogen as much as uranium or whatever you like, heavy elements, treating it fully relativistically means solving the Dirac equation. So there's no problem with this.
Okay, and question is the following. Actually, in biomolecular studies, and in particular in pharmaceutical industry, already for something like 20 years, this type of studies have already been very extensively carried out.
Yes.
And in particular, pharmaceutical companies put a lot of money into such studies. The question is, and in particular, such a method which is called routinely QSAR, qualitative structure activity relationship, which actually contains 50 different approaches, is quite well developed. The question is, do you monitor what's really going on in this area, because you can actually adapt relatively easy and not develop actually the second time the same approaches, right?
No, I think makes no sense to reinvent the wheel. Yes, I mean we are pretty late, let's see, in our community. Also, the error quantification in chemistry, so to say which code and which basis set gives which kind of accuracy or so, or precision, has been started decades ago. Also, machine learning and these high throughput calculations in pharmacy has been done a few decades ago. Also, machine learning has been employed in chemistry much earlier. The problem is that materials are much more complicated. So, for instance, you can predict the total energy of a molecule, given you have other molecules around that you can use for training, with very, very high precision. Okay? Because you only need to know basically the configuration to your nearest neighbors or something like this, called the Coulomb matrix, if you like. For materials, this doesn't work at all, because you need to take into account this long-range interaction between different unit cells, and to somehow cast this into a simple descriptor is a nightmare. This is really, really tricky, and that's why we seemingly reinvent the wheel, but in practice we don't. I think we really need to go through all this, because there's not such a simple solution for materials.
Okay, thanks.
Okay, let us thank to Claudia. And the colloquium is concluded. Thank you.